So let's assume that the value in y is 60 and the value of x is 60 and the value of y is 55. So in both cases is a value that is higher than the mean. So it will be a value of 10 for x because it's 60 minus 50 is 10, and a value of 5 for y because 55 minus 50 is 5. So we've got 5 times 10 is 50. So the values that are in this quadrant will be positive because we are multiplying two positive values. And the higher the difference from the mean in both cases, the higher that number will be. Now, suppose the value, one participant scored 20 in x and 30 in y. So that 20 becomes negative 30, and the 30 becomes negative 20. So negative 20 times negative 30 is negative 600. Sorry, not negative 600, it's positive 600 because we've got two negative numbers, and when we multiply them, then it becomes a positive number. And that's what I wanted I show here. When the values of x are lower than the mean and the values of y are lower than the mean, they will be in this quadrant. So can you imagine if the values are in this diagonal, then you're going to see values here and values there. And so your most of the values will be positive when we do the multiplication. On the other hand, if the values are in this diagonal, we will have values in which in one of the variables is a positive value and in the other variables is a negative value. Likewise, same here. And therefore, when we multiply those values, the values will be negative. So if there are more values in this diagonal, then the correlation will be negative. And if there are more values in this diagonal, then the correlation will be positive. So that explains why you would get positive numbers if there is a positive correlation, positive association, because if the values are in these two quadrants, that means that higher values of x, you expect higher values of y. If the values are in this quadrant, then you expect for higher values of x, you expect lower values of y. And that's the reason why it works. And then when you obtain that covariance will be a value, positive or negative, but we cannot compare with anything because it depends on the number of observations and it depends on the possible values in the variables. So if you have a variable with which possible values are a small range, and another variable that the possible values are it's a long range, then the covariance will be much larger in the variable with a large range of values. So the covariance in itself, yes, is an important measure of how the variables covary, but they are not standardized. In order to standardize, we need to obtain the standard deviation of each of the variables and then obtain the product. So when we divide by that, then it gives us a standardized value that it goes from -1 to +1. So that means that the covariance can never be a higher value than the product of the two standard deviations. It could be the same value, in which case the correlation will be either positive 1 or negative 1. What are the two important components in correlation? Well, one is the variability of the data, accounted for by the regression model, and the other one is the slope of the regression line. And as you can see here, I'm relating, the question was about correlation, but I am answering with regression. This is because correlation and regression are intimately related. They focus on different things, but the process of or the essence of the two are very, very similar. So what is linear regression? How does it differ from correlation? So in linear regression, in correlation, we obtain one number, and that number gives us an idea of the strength of the relationship between two variables and the direction of the relationship, whether it's negative or positive. That's all. Just one number that gives us very important information. Regression, on the other hand, gives us a line, and that line has the one intercept, which we call B0, and a slope, which we typically call B1. And the intercept is the value in the y-axis that corresponds to a value of 0 in the x-axis. So here x is 0 and y is this value, and that's where the regression line intersects when x equals 0. So intersects in the y-axis when x equals 0. So that's the B0 in the correlation, in the regression equation. And then the slope indicates how much y increases as a function of an increase of 1 point in x. And as you can see, if we've got a line that goes like this from one point to the other, that means that when we go in y from 0 to 100, in x we go from 0 to 100. So we do the change in y, in this case was 100 points, divided by the change in x, which was 100 points, that's 1. So then the regression, the slope will be 1. Here you can see that when we go from 0 to 100 in x, in y the range is a bit lower, so it goes from around 25 to 75. So that's 50 divided by 100, that is 0.5. So the slope in this case will be 0.5. And one thing that we need to use to calculate what we call the R-square to determine how much of the variability of the data, the variability in variable y, is explained by the regression model. So what we need to do is to calculate for each of these observations which has an x value. So for that x value, we calculate what's the difference between the mean of y and the value, predicted value by the regression. That's what is shown here. And then we calculate the square of that distance, that is to get rid of negative signs. And then we sum all these values. So that's the sum of square of the regression. And the sum of square of the residuals is the difference between each observation and the regression. So the more distance there is between the observations and the regression line, the worse the model is. And the closer the observations are to the line, the better the model is at predicting observations. Okay, what's the sum of squares total? So I show you the sum of squares of the regression and the sum of squares of the residuals. So what's the sum of squares total? So the sum of squares total is the total variability of y. And it's calculated by, for each of the orange dots, indicating what's the distance between that dot and the mean of y. I mean, that's the way we calculate the variance and the standard deviation. We subtract the mean from each of the possible values, then we square them, and then we add all those values. And that's the sum of squares. So the sum of square total will be this in this case. Sometimes we continue a bit further and we divide by the number of observations minus 1, and that gives us the variance. And then sometimes from the variance we do the square root of the variance, and then that gives us the standard deviation. Okay, so sum of square total then is the variability of y. And we can separate the variability of y into two variabilities. One is the variability of the regression model, which is the difference between the mean and the prediction of the regression model, plus the sum of squares of the residuals, which is the difference between the prediction and the actual data. And if we divide the sum of square of the regression over the sum of square total, this is what we call R square. And it tells us how much the regression accounts for the variability in y. Okay, let's see the slope of the regression line. So, as I mentioned before, if the regression line is in this 45-degree angle and it goes from bottom left to top right, then there is a tendency for the correlation to be 1. Why is that? Well, because it's difficult to have, if we have this line, it's difficult to have variabilities. Like, for example, values that correspond to, for x 100, I predict a y of 100. Well, the prediction could be erroneous, but in this case, it could only be erroneous by overestimating the values of y, because I can have values of y lower than the prediction, but I cannot have values of y higher than the prediction because I reached the limit. So if this is the case, then my value should be, the top value should be very, very close to the line. And same with the values close to 0. My prediction could be R only by underestimating the values of y, but it cannot overestimate the values of y because there are no more values. So when we have a line like this, it's because there is very, very small variability in the data. So usually, if there is more variability, the line it's either rotates over there, and it's like this, or rotates towards the mean of y, and it would be something like this. Okay, so this also tends to be a -1 correlation because it's in the 45 angle, but it goes as the values of x increase, then the values of y decrease. This one and that's why the two important values for a correlation is, how steep is the regression line, but the most important is the variability from the observation to the prediction of the model, and what we call residual before, and we calculated the sum of square of the residuals. So in this case, this is typically very unusual, but it happens. The values are all in the line of the regression. So in this case, the correlation will be 1, because I can predict perfectly each value of y based in the value of x without error. Now, this is the same regression line as before, but the values are separated from the regression line. So that means that in this case, the correlation will be much lower than 1. It won't be 1 because there is variability, and so the sum of square of the residual increases, and so therefore the sum of square of the regression model relative to the sum of square total decreases. So then the correlation will be lower than 1. And this is a special case in which we can predict perfectly for each value of x, we can predict the value of y, but because all the values of y are in the mean of y, then the correlation is 0. So there is no correlation. There is no association actually between the two variables, because when there is association, you expect that if one variable increases, the other one either increases or decreases. In this case, you increase the variable of the value of fx, and the value of y doesn't change at all. So this is a special case that even though all the values are aligned, are in the regression line, the correlation will be 0. But as you can see here, we move a little bit, the top values go a little bit high and the bottom values go a bit low, and the correlation passes from 0 to now being 1, because we've got a perfect prediction, but the values of y are not all in the mean of y. What issues should be taken into account when running correlation? The range of possible values. If you restrict the range, you're creating problems. So in this case, we've got a correlation, which is a decent value. And then if we decide to only observe the data of the higher performers in this variable, in the dependent variable, and in this case, we would see only those participants that score very, very high in the dependent variable. Okay, if we look at the correlation, now it disappeared. The correlation disappeared, and that's only because we restricted the range. So we need to know very well that if we are using all the range of possible values of the dependent variable. Nonlinearity. It doesn't make any sense to calculate a correlation coefficient here, because it will be 0, but actually these two variables are strongly related. The problem is that they're not linearly related, so I cannot use a line that predicts the value. I can use a curve, but then it's not linear regression and not correlation. So correlation assumes a linear model. The heterogeneity of the samples. So let's say that in children, in red, there is almost no relationship between the two variables, but in adults, in black, there is a strong relationship between the two variables. And that the only way we can do that is visualizing or we can do by identifying the participants' gender before and then running the correlation separately. So this is very important because we need to understand why, if the relationship between two variables differs in these two groups, why is the case. And so, but this, if we completely ignore the sex in this case of the sample, then the correlation is very low. But if we don't ignore that, the correlation in the black dots becomes very, very large correlation. And extreme values, in this case we've got a correlation of 0.22, but if we add one value to the right, top right, then all the other values, they don't look the same because I changed the x-axis, but now the value in the top bottom it's pushing the correlation to 0.68, which is not realistic. So in those cases, how to deal with the outliers? Sometimes is eliminating the outliers, and in other cases we need to transform the variable. We transform into a logarithmic scale, for example, and then we run the regression after the transformation. Another question is, how do you determine if a correlation is significant or not? And the answer is that we convert the R score into, which is the correlation coefficient, into a t-score using this formula, and then we compare the t-score obtained with a t-distribution, and if the probability is lower of obtaining the t-score we obtain in our sample is very low, in considering that the t-distribution comes from a population in which the correlation is 0, then if the probability that our study comes from that from a sampling distribution that came from that population is very low, then we reject the null hypothesis. We say, no, this doesn't come from that population, must have come from another population. So therefore we reject the null hypothesis. Finally, what is linear regression and what are the differences and similarities with correlation? So we already went through the regression line because I needed to explain the linear regression in order to explain correlation. So now when we explain linear regression in itself, we add a bit more details, but I've already went through this. So that's what I mentioned before. Y hat means that we are predicting y. So the prediction of y is given by this formula. B0 and B1 are parameters that are estimated by the data. How are they estimated? Well, I'll show you the exact calculation, but this equation will create this line here. And we need to come up with a line that minimizes the error of the prediction. So we can draw an infinite number of lines, but there is only one that minimizes as much as possible the distance between the dots and that line. So the value that intersects in the y-axis the value of 0 of the x-axis, that's the intercept. And in this case is 1,844. And the amount of increase in the y variable as a function of one unit of increase in the x variable, then that's the slope. And the way we calculate the B1 and B0 is B1, we have to obtain the covariance of xy, and then we divide that by the variance of x. So if I return to the previous slide and we calculate the variance of x, so how dispersed the values of x are from the mean of x, and then I use the covariance of which is something about the relationship between these two variables, we divide that by the range of possible values of x, and that gives us the slope. And then when we obtain the slope, then we calculate the intercept without any problem. So because we need this y bar means the mean of y, and x bar means the mean of x. So basically we calculate with the slope that we calculated there, we multiply by the mean of x, and then we do mean of y minus that value. And that is the value that is b0, and that's the intercept.